东金融。Snack? Cookie for snack? I thought you were doing the image originally, but now you are in the racing.
Always racing.
Oh.
Last day.
It's going where the money is.
Yeah.
See, there's money in horses. Just
No,
go to horses.
I and I were talking. We're in the wrong business. They take 18%, take it to track. We should just open a track.
Yeah.
Forget all this.
Yeah.
You deal with it.
You know, it's a non-profit.
Non-profit?
All the extra money they make goes to the government and to charities.
Oh, really?
Yeah.
Oh.
They pay like 72% of their income to the government. Taxes.
Oh.
And whatever is left, charity. It's really cool, actually.
How about in Hong Kong? I think gambling, horse gambling is big in HongOng and Macau.
This is the Hong Kong, what's it called? Hong Kong
Jockey Club.
Jockey Club.
Oh, okay.
Yeah, that's what it is.
And they have a monopoly. I don't think there's any other horse racing allowed, if I understand it correctly.
Oh, okay.
They're the only place to go.
I see.
That's why they have so much good data.
Monopoly, yeah. Lottery is also big in Hong Kong, yeah, doing lottery. Yeah.
The gambling in China is a big part of the culture.
Not, but in Macau is the eastern, Las Vegas, yeah.
Heard about it.
Yeah. Okay, let's start our lecture. So this is the last lecture of the deep learning track. And today we are going to focus on deep learning and its relationship with time series. So even though the technique we talk about is applicable directly to time series, but it's also applicable to many, AI tasks, like natural language processing tasks. So right now, the long short-term memory neural network is a hot topic, a buzzword in the deep learning, community, and there are many new applications that we cannot talk about. So today I'm going to stick to a foundation, and the slides, there were about 70 plus slides, so I'm not going to go through all of them slide by slide. I really want to spend some more time with the lecture codes. So first, let me review what will be discussed today in today's lecture. First, we review the classical time series framework that we talked about in the previous 2 days, namely the ARMA philosophy, and what's the key points and what's the weakness. And then we talk about a little bit about neural network and nonlinearity. Then we can make a jump from the so-called feed-forward neural network, the classical neural network, to the so-called recurrent neural network. So today's focus point will be on RNN, recurrent neural network. But classically, the recurrent neural network was developed, its idea was, developed in 1980s. And, but actually, your realization was only realized after the introduction of long short-term memory neural network. And later, the cousin is called GRU, Gated Recurrent Unit. And I will spend a little bit of time talk about long short-term memory neural network, what's its cell look like, and probably don't have time to talk about GRU in particular. So this is today's game plan. Then we'll move on to the lecture code to at least demonstrate to you how it's done in TensorFlow. So we are going to compare the time series task and the machine learning task, which we call PAC, and the limitation of ARM and ARIMA. So within the linear regression and other machine learning model we have taught you, we are actually using some implicitly known as a PAC framework, properly approximately correct framework, that it allowed you to do cross validation, etc. The underlying assumption is that all the samples have to be, the underlying assumption of this framework is that all the samples have to be independent. In the earlier linear models, you can assume that all the residuals are IID independent, and later in random forest and the survival machine, etc., you do need to assume that the samples are independent in order for you to do cross validations. But if you find that systematically the samples are not independent, for example, if you are doing purchases, or same person do many purchases, or the same patient have many data points together, and there's no way that these samples are independent. In that kind of situation, you do need to modify your framework to adjust for the situation. But that's the general framework for us to discuss the cross-validation and the grid search, etc. And this assumption is often implicit when we perform cross-validation and find the best model available. And if you have a validation of the assumption, what happens is that you can still run the cross-validation, but your cross-validation would not find the best model. The cross-validation still can be done, even if the assumption is seriously violated, but what will happen is that you will find a suboptimal solution, which often lead to, overfitting in our sample data. But on the other hand, the time series data is, roughly speaking, data parameter by time, which often displays strong inter-time span correlations. That means, by definition, time series data is nowhere you can treat it as many independent samples together, because they often correlate to each other strongly. So in such a situation, that the PAC framework is violated severely. That's why actually at the first approximation, we want to put time series aside and discuss individually. But indeed, many of the framework that many of the machine learning algorithms you use can be also applied to for time series prediction. Like I think Michael actually in his 0.72 coding challenge, besides using the classical ARIMA, or he also used boosting tree or something to do a time series. It's perfectly legitimate. But you need to do spatial treatment, and before you do that, and the time series data often have a strong inter-time span correlation. And therefore, naively, you cannot treat each data point as an individual sample, and you won't work in that way. And one example that I already showed you is the SMP 500. SPY is the ETF version of SMP. And then starting from 1993, that's where SPY starts as ETF. Then it will go through the internet bubble and then crash. And then there's a second leg. This is where the housing bubble starts. So it turns out the crash of the bubble is highly correlated to the fact that during the bubble time, a lot of people see that the price rise crazily, and they also jump in, and they cause a snowball effect that the price rise even higher. You can gauge that during the time of the early period of 1990s, the annualized return of S&P is about 23%, excluding dividends. But long-term average of the S&P, if you count for the last 70 years, 60 years, 70 years, is only 7% without dividends. So they are triple the regular amount. And where do that kind of return come from? The only explanation is people jump in and cause the bubble to form and a snowball. And the crashing of the bubble and the bubble forming, they are intercorrelated to each other. There's no way to treat the whole thing as independent sample. It's completely wrong to do that. So for that reason, time series data need to be treated differently from regular machine learning methodology. And therefore, when you want to apply XGBoost, random forest, etc. to time series, it's okay. There are cases you can apply this kind of machine learning algorithm to time series, but you need to take care of something before you can apply them. So this is one main reason that time series modeling is often viewed as a different topic. So in schools, people usually teach time series analysis differently from machine learning, even though these two fields kind of overlap to each other. And the people actually apply ideal neural network to time series long time ago. But nevertheless, time series is an individual topic. In today's lecture, pay attention to neural network and its application to the sequential or time series forecast. The main focus of today's lecture is a special case of neural network called RNN. RNN is called a recurrent neural network, and its extension, long short-term memory neural network. So RNN is a general prototype, but without the long short-term memory neural network, the earlier day RNN is not very useful. So the real breakthrough of the RNN fields is the invention of something called long short-term memory neural network, and which is right now a buzzword in deep learning community. And people even use it to develop a recommendation system. So there are wide applications that of this kind of architecture. So we will pay some attention to long short-term memory neural network, also addressing some historical issue of RNN. So LSTM is a special case of RNN. And time series prediction is widely used in econometrics, engineering, and business applications. And predicted the future behavior of economical indexes, stock prices, electronic signals, and business inventories profit are vital to the success of many industries. So time series forecast has a lot of wide applications in industries. In terms of interview and jobs, right now we are not seeing that a lot of jobs which warrant 100% time series modeling. But we have examples that people get hired into Pepsi, and in that team, they are actually the coding challenge is time series, 100% time series. We also have example that people get and try to get interview with 0.72 kind of hedge funds. They specialize asking questions in time series. And also our alumni, some of them work in the fintech industry, and they also specialize in time series. So there are many use cases of time series. The most interesting case is that one of our former students who actually get hired into the music industry. And believe it or not, 1/3 of his job become the time series modeling. But in terms of job description, you don't never see it. But in terms of their real job, the reason that they care about different kind of music, like rock and roll, and or blues, jazz, this kind of music, and they care about how different kind of music, how much time does it take for the music popularity to drop? Because the radio station all throughout the country is going to how do I say, the music will be circulated to the audience, and they will start to do that when the popularity die off. How much is the half decay? They find that it turns out different type of music have different kind of profile. So this kind of thing can be used as intelligence for them to develop a better program. And it turned out to become time series problems. So time series has a lot of different kind of applications, and but I would imagine people would need time series sometime in your career. But if you go to finance, typically 100% of the time you will deal with time series every day. In the time series lecture, we have discussed the classical ARMA, and VARMAX framework to deal with time series prediction. What does ARMA stand for? ARMA is a combination of AR time series and the MA time series. And what's the distinction between ARIMA and ARMA? ARMA handle stationary time series. If a time series tend to be bounded between a finite range, have a finite and fixed mean, finite and fixed variance, and finite and fixed autocorrelation, etc., you can study it using the classical ARMA. But what if the time series is not stationary? Example is like stock price. It tends to go up to infinity when time goes to infinity. In that kind of situation, ARMA is not good enough. You have to use ARIMA. So ARMA and ARIMA. Then what about the VAR and the VARMAX? The VAR is the vectorized version of AR time series. AR time series is auto-regressive. That means the past value of the time series can influence the future value of the time series through a linear relationship. And what VAR means is you not only allow a single time series, but you allow multiple components of time series and to occur simultaneously, and the past value of the vector can affect the future value of the vector. So in terms of when you write anything on your resume, expect people to ask you this kind of question. You write the neural network, you write long short-term memory neural network, can you tell me what it is? Just orally. So people can ask this kind of random forest. And what is random forest? For some period of time, that people like to ask neural network. This is really very hard to predict. It really depends on the nature of the interviewer. And if he is interested in neural network, he will ask every candidate about neural network, and you cannot stop them. So whatever things you write on the resume, be sure to have a defense, oral defense on that. What does VARMA stand for? VARMA means the vectorized version of ARMA with the exogenous features. The exogenous features means not only you are using the past value of a time series to predict the future, you are allowed to use the outside features to predict the future of the time series. The example I gave you is like housing price. If you are aiming for predict the housing price as a time series, you can use the past value of the housing price to predict the future of the housing price, but you can also use outside features like interest rate, like local labor market condition. That kind of macroeconomical indexes to predict the house price. And that kind of feature doesn't belong to the house price time series itself. It's called exogenous. These are economic terms, that features. So this model allows you to actually model a time series as a dependent variable and using outside features. And this is sometimes the key for your success. And actually in Michael's coding challenge, he used this feature, this kind of models. And in a lot of financial time series, this is very crucial because financial time series is notoriously difficult to predict. If you just use the ARMA, it could be that your R-square is so low, like 2%, 3%. Sometimes you need to add exogenous features in order for the prediction, much more accurate. For example, if you would predict stocks, you can use the sentiment of some kind of Twitter, that people tweet each other about the stocks and give different opinions. And you can actually do sentiment analysis on that, and maybe they can fit into the stock price eventually.
So that would be VARMAX?
You can use VARMAX. So for example, if you have 100 stocks and use the past value to predict the future, it will be VARMAX. But if you also include the sentiment from the outside, the trader, how is the trader's opinion about the stocks? Or how's the analyst's review about the stocks? This kind of information are not price information. If you use it to predict the future price, it becomes VARMAX. So I'm not doing the detailed work for you. I just lay out that conceptually, this kind of thing is very natural. If the original time series is non-stationary, then the repeated application of the difference or delta operators often change the time series into a stationary time series. So even if you apply the so-called deep learning to time series, you still need to do the same trick. Check whether the time series is stationary or not. If it's stationary, you can use the deep learning technique to handle that. If the time series itself is not stationary, you need to differentiate until it's stationary, and then use the deep learning techniques to handle it. There's no way you can use a deep learning technique to track a nonlinear time series which is non-stationary, because it's moving all the way. And the machine learning algorithm, no matter it's deep learning or random forest or support vector regression, they can only interpolate. They cannot extrapolate. It's very difficult for machine learning to extrapolate to the sample point outside its domain. You are asking some question you never see, and it's not going to be able to answer. And the only exception is linear regression, can do some kind of extrapolation, doing a linear trend projection. So, for example, if you find that you take a log on the stock price and say the trend look probably approximately linear, you can say if the linear trend persists, what will happen 100 years later? You can do that kind of question. But you cannot ask the random forest or ask the XGBoost to predict what will happen in 100 years. It's not able to do this kind of thing. Because that kind of thing is already grow out its domain.
Is it because you have non-stationary mean?
Yeah, you have non-stationary, so it's keep moving out of your range. And the machine learning only can learn for everything in a box. Remember, tree will learn things in a box. When you go out of the box, it cannot think out of the box, and therefore you cannot predict. So you need to always treat the time series, check whether it's stationary or not. If it's non-stationary, bring back to stationary by differencing a few times. Once it's stationary, you can deal with by the standard technique, either deep learning, machine learning, or traditional time series technique. So this step is kind of crucial. So stationary time series, the classical autoregressive and moving averaging model, AMA, model time series in terms of very simple linear model. So AMA is actually a linear framework. And as Michael has pointed out, it's closely tied to multiple linear regression, at least AR part. So technique is there, I mean, it's a long time ago. But right now, it's still become a classics. It's not without a reason, because one benefit is that because the linear model, we know inside out in terms of linear model, and therefore we can estimate confidence interval, etc., and analytically. And this become a major, strength of AMA model, that you can estimate the probability, how confident you are with your prediction. And that kind of estimation, and you cannot do with the nonlinear model. I also mentioned that ARIMA and AMA model, the estimation involve a technique like linear regression, and also in the MA part, you cannot do linear regression, but it's based on maximum likelihood estimation. Maximum likelihood is also an important technique. And I think 2 days ago I checked with the student from previous cohort, and he actually went to an Uber interview, and they asked him questions, even for the phone interview, they already asked him questions about probability. So do not think that machine learning is only on fit and predicts. This is not the case. People also care about your foundation. It's okay? So I want to change your perspective, that in your project, You probably do a lot of, I mean, dropping your RMSE and compete for that. But this is not the only game in town. In the interview, people can ask whatever question they want, and people even in the phone interview, that's the first step, already screen candidate by asking you simple things in probability. So that's why actually on the midterm or in some of the practice exam I'm giving it people, I include things related to probability. Make sure you brush up that kind of techniques. It's okay? So do not treat them as something that the instructor told me something and then eventually now I do fit and predict. This is what I do. No, everything in the package you need to know. But in terms of deep learning, I won't say at this moment it's mandatory. Maybe 10 years from now, everybody will know deep learning. And this becomes a scikit-learn of 10 years later. But right now, I would hope you to treat it as a jump start. It's okay? But the more fundamental parts of our, of whole Python machine learning and ARM machine learning, the more basic one, you need to really take care of that. Because in real life, people can quiz you in the phone interview, in real interview, and you can get shocked. You say, what? You asked me this. But my score is the lowest in my class. My IMS is the lowest. Other people get 0.12, and mine is 0.10. But that's why I don't care. Usually your mindset has to be changed before you go into an interview room. That understand, I think Vivian is giving out a lot of information about the coding changes of the different companies, but there are different sample points. Try to form a view on what should be prepared. It's okay? So the weakness of ARIMA and ARMA and VAR and VARMAX. So we talked about this 2 days ago. We talked about this yesterday. But the fundamental assumption of them is that the underlying generating mechanism of the time series is fully linear. This assumption makes life very easy. But unluckily, it's not always realistic. Especially nowadays, a lot of breakthrough in the AI or in deep learning happen because you can begin to take into account that things are nonlinear. The most famous example of nonlinearity is our brain. Our brain doesn't think linearly. Our brain naturally is nonlinear. And that's why deep learning is trying to mimic human behavior in many different ways. So let me give you some example of nonlinear time series. The first example I give you is, you will see more examples in the lecture codes, is that recursively, if you don't have this term, xi is equal to minus 0.2 xi minus 2 plus epsilon I, where epsilon I is the Gaussian random noise, which is also called white noise. This should be an AR2 time series. But because you have a sine square of xi minus 1 here, this makes the time series fully nonlinear. Usually, you do not have that kind of luxury to know about the formula on the right-hand side. In the time series question, what happens is that you only know a value of each time span value, like this, you know about this, but you do not know what's the underlying mechanism to generate it. And that's a reverse question. It's very hard to guess what would be the right way, because you can use sine, you can use cosine, exponential, or even some unknown function to generate, and it becomes very hard to guess. And this is an example of a nonlinear time series. The time series is a nonlinear AR2. It depends on the recursive terms, that the leg 1 term and leg 2 term, but the dependence is not fully nonlinear. And if you look at the time series like this, if you only see the picture, you probably even don't know that time series is nonlinear. You probably still try to fit it by AR2. But it's not going to do very well, because the underlying mechanism, once we know that it's nonlinear, cannot be modeled by AR2 that well. It's okay? So that's why actually sometimes people does need to go into a nonlinear domain and to do the model. But this time series, except this white noise term, this formula over here is deterministic. In the case that you have a very complicated deterministic time series, you can use support vector regression to do it. It turned out before, deep learning come along, become popular, support vector regression used to hold the world records in handling nonlinear time series.
Is that how you would solve for X's equation? Is you support vector regression?
Use support vector regression to model this expression. If you use RBF kernel, and it's very robust, you can try to solve for this kind of equation. Yes, if the thing is deterministic. But if you have a lot of non-deterministic part, like the big noises, that support vector machine is not known to handle that very well. Then the classical ARMA can help to handle that parts. Because maybe the noise is not white noise, maybe the noise have internal structure like MA time series. So you probably need to combine both. But if you have a question which is like a robotic arm, like motion of robotic arm, which is deterministic, that kind of thing can be modeled by a support vector regression or neural network. So I'm not saying that that kind of technique is not useful. It indeed is very useful. And the support vector regression, at least for a while ago, it was the world records in modeling all this kind of deterministic time series. So this is an example of nonlinear time series. And clearly go beyond the AR2 we talk about in ARMA or ARIMA. And it's mentioned ideally a long short-term memory neural network. That's today's main character. So we have the many models in machine learning with high model complexity like random forest, gradient boosting, support vector regression, and neural network. All can be used to study nonlinear time series. So which approach is best often depends on the nature of a given time series, which can be found out only through empirical trial and error. That means there's no single tool which works for all time series. And they repeatedly find out it's true. So you can Google, there's a test called M3 test and competition. I mentioned they held 3 different competitions, not cargo. Is the competition among the time series researchers. They use a few thousand time series from different domains, business domain, but like electricity, generation, etc. All different kind of time series. They found that the different time series should be handled by different tools. There are some tools good at handle certain kind of time series. But overall, if you want a single tool which can handle multiple kind of time series, usually you will go down to the classical linear type of time series or its variants. It turns out some tools like neural network or support vector regression can handle some kind of task very well, but you fail miserably in other kind of tests. So this is what happens. So when you are using machine learning algorithm to train a model in time series task, it's possible, but it's a little bit ad hoc. Nobody will give you a recipe that this model is good for all time series. It's almost like impossible. In recent years, long short-term memory neural network is the extension of RNN. Recurrent neural network has been very popular in deep learning, in dealing with NLP, natural language processing, and time series modeling. So in a sense, natural language processing and time series modeling are two sides of the same coin. Why? Because in time series prediction, you have a sequence of real number. And there's it's called sequential regression test. But in the NLP task, each token, English token, is viewed as a categorical value. And how many possible values are there depend on your vocabulary. If your vocabulary use like 2,000 English words, then you have 2,000 possibilities. And then you have a sequence of this kind of English words, English token. After you standardize them, called demonization, etc., then it becomes a discrete sequence. And then what you are doing is a sequential classification task. So NLP test is a special case of the sequential classification task, and the time series task is a sequential regression task. And they are cousin to each other. They are cousin to each other. And you will find that a lot of things that in NLP have an analog in time series, and they are not a coincidence. Because those people who have learned and invent things in NLP, they already studied time series and borrow idea. And one example is that some of you probably know that in English or in the NLP, there's the so-called n-gram model. Each time you look at n consecutive words and use it as one feature for prediction. And the next time you move your window and then look at the next sequence of n consecutive words. And that kind of thing is called n-gram model. The easiest one, such kind of model is called 1-gram model. Each one you only use one token, one word. And we did use it. In our machine learning lecture, we already told you that by counting the number of words, then you can actually form a word counting vector. And that's actually the basis for classical analysis. For example, if you want to do a movie review or a business review, etc., that's called 1-gram model. Besides 1 gram, you can use 2 gram. Each word is like I like or like data, and then data science. Each time you look at 2 words. And this is at the analog of the moving window we talk about in time series. In time series, we have the so-called moving window average. The kind of concept of moving window. Or later, in the so-called convolutional neural network, the concept of convolution is also based on moving window. So everything really comes from time series. And those people who actually make contribution to NLP or convolutional neural network, they are trained in time series. Suppose you go to a PhD program, the time series is a must for you to go into this subfield. So there are a lot of relationship between NLP and the time series. So even though today's lecture is about time series, a lot of concept can be moved into NLP as well with some modification. So long short-term memory neural network, which is a special case of INN, shine when the time series display the long-range time domain dependence. So there are many kinds of neural network architecture you can try to model nonlinear structure. People may ask you, why do you insist to use long short-term memory? And the answer, the main reason is long short-term memory neural network shine when the time series displays long-range time domain dependence. Why? Because long short-term M means memory. It can have memory to memorize what happened a long time ago. And you can use that memory to do prediction. And this is something that the classical ARIMA cannot do. For that reason, long short-term memory neural network become very popular nowadays as a solution to problems which have a long-term memory. For example, you may want the neural network to memorize this year's Thanksgiving when you want to actually study this year's Thanksgiving. This is already like 365 days ago. Usually, this kind of window is too long for you to consider into a time series because if you use ARIMA, your P need to be at least 365, but in order for it to work. And then you overfeed your model because there are too many features. But long short-term memory neural network can memorize what happened a long time ago, or can also forget it. There are some kind of switch, on and off switch, allowing you to forget or remember some kind of past feature. If you screen the data and find, well, this feature keep on happen again, or this feature keep have association with the target repeatedly, I can choose to memorize it and then use it for prediction without introducing too many unnecessary features. Is the concept clear? So if I want to use last year's Thanksgiving sales to predict this year's Thanksgiving sales and the moving window, if I do a ARIMA model, my AR time series p-value, not p-value, p, order have to be very large. If I do that, I'm also including a lot of chunks in the middle, which make the model overfitting. But long short-term memory neural network can solve the problem. So if you train suitably, you can memorize the things happened long time ago. And in our real life, besides time series, there are a lot of situations that kind of pattern exists. For example, in psychology, it's well known that the childhood experience affects how does an adult behave. So all of us actually somehow are shaped by our childhood experience, at least according to an expert. That kind of experience happened a long time ago. And how do you use a model to model that? So it turns out you need to have some kind of long-term memory in order to model this kind of long-range time domain dependence. And I use cigarette smoking as an example, that when you smoke cigarette for 30 years and eventually get cancer, that's not an immediate consequence, right? It's not they smoke today and then tomorrow you'll get cancer. Often the causality is very slow. So this is a long range time dependence. And the personal finance, that you overspend too much money and eventually lead to bankruptcy a few years later. This is also a situation that is not immediate. In the contents of NLP, in a document, you may talk about one thing. Maybe in the first paragraph, I talk about Donald Trump. And then in the second paragraph, I talk about something totally unrelated. And then after many paragraphs, I come back to the original topic. So I talk about how does Donald Trump policy affect US economics. So it's very hard for a traditional method, no matter how many grand do you use, 2 grand, 3 grand, 4 grand, to detect this kind of structure, which is happened long ahead and then reoccur later. That kind of structure can be detected by long short-term memory neural network. So this is one benefit of LTSN, long short-term, I should say LSTM, this is misspelling, LSTM, neural network, and how actually right now shine and become the darling in deep learning field because it have this kind of memory. And after long short-term memory neural network, people also try to extend it to invent a neural network which have other kind of memory and do a lot of non-trivial tasks. Classically, you would not imagine doable. So both the INN and its long short-term memory variants are among today's main topics. But the long short-term memory neural network originally was not invented because have this nice property. It was invented to fix the shortcoming of the generic INN. So I'll tell you a story, what's going on. How or why? I'm not going to give you a detailed architecture, but why people invent long short-term memory in mid-1990. And the time of invention of long short-term memory is almost the same time as support memory machine. But when support memory machine was invented, it immediately became a popular algorithm. But it takes a long time, take about probably like 10, 20 years for long short-term memory neural network, its value be appreciated fully in the industry. And now it's very important. So we have to understand what is the INN and how does long short-term memory improve on INN. So these are two main goals. So in case you want to write this on your resume, that you would need to explain to your interviewer. So people can, as I told you, people can ask you whatever thing appear on your resume, either through like a coding challenge or sometimes just orally. Yes?
Do you think it's okay to write, for example, RNN on your resume, even though you haven't really done a project?
It's fine, but try to make you. I was trying to make my wording slightly more conservative. I say some exposure to INN, it'll be fine, right? Some exposure is fine. But you want to say expert in INN, then you are inviting challenges, yeah. Right? And what if you ask question you cannot answer, and then you'll backfire. I'm not saying you cannot write on your resume, but when you write responsibly. Because my general impression is, of course, your interviewer have different kind of character. Maybe they all like that kind of thing, I don't know. But generally, people do not find discrepancy between your ability and what you claim, because it's a sign that you are not telling the truth. When you create doubts in the interview, it becomes very subtle. So try to be as straightforward as possible. Even if you don't know anything advanced, you can just say, I'm clearly, so right now I'm just learning machine learning for 2 months. So my focus is on the basics. I want to make my basics solid. So I don't know that much about the deep stuff. That's fine right now at this moment. Because this field is relatively young. And people understand that you only spend 2 months in machine learning. But if you brag about many things that you cannot support, you will create a different impression on people. So So let me summarize a little bit about probability. So the time series is a sequence of real value. And as I say, if you look at the sentences in NLP, it's a sequence, but the sequence are taking the taking the discrete values. So the only difference between time series and NLP is NLP handle discrete or categorical values, and time series handle continuous values. And the first order business, often you want to ask yourself the following conditional probability. How could I use the information of the previous few tokens or timestamps information to predict the next? And this is formulated in terms of the conditional probability. To code or formulate this conditional probability become the first order business both in time series and also in NLP. So if you go to NLP literature or textbook, this is usually known as forming a hypothesis on this conditional probability is usually called a language model. A language model. So a time series situation, you want to understand the probability, the conditional probability, and in a spell case, you go back to the more classical framework like ARMA or ARIMA. Even though unconditionally, the variable may not be a Gaussian distribution, but conditioned on the facts that the previous lag information is already known, you all or often assume that the residual is a Gaussian distribution. What it means is that you are assuming that the uncertainty associated with the target value xn, once you fix your initial values, is only the residual, which is a Gaussian distribution. In that kind of situation, there are two simplifications you can do. First, you know that a Gaussian distribution is uniquely characterized by two things. It's mean and its variance. So this is an important concept. Any Gaussian distribution, once you know its mean and the standard deviation, which square to variance, then that Gaussian distribution is uniquely determined. In that kind of situation, to make hypothesis on the Gaussian distribution can be simplified to make hypothesis on the mean value itself. What's the mean, conditional mean of the random variable, which is the mean of the Gaussian distribution. And that's what we were doing in our previous ARIMA lecture. In our ARIMA and ARMA lecture, we will try to model this mean. Remember when we talk about the AR time series or ARIMA time series, used it to fit the stock price. The stock price, actually, we predict for some model, the stock price will keep horizontal. And that's the prediction of the mean value. It doesn't really think that it will go, nobody will think that stock will be constant. But this, what model predict, the mean value will be, in that model, will be a constant. So the time series text, the key points to predict the mean value, conditional mean of the time series value, future value, based on the historical information of the past. And one thing that the neural network is so useful in this is in the 1990s, neural network is proved by mathematicians to have something called universal approximation property. This is something called universal approximation property. That neural network can be approximate any function you like with arbitrary accuracy. You draw a function, you don't know how to, even though if the function is smooth enough, you don't know how to write a formula. You can use a neural network to approximate it to arbitrary degree. This is known as the universal approximation property. So after that, in 1991, once people proved that, they sent a shock wave among the neural network researchers. And that neural network at that time become the buzzwords. And then it was killed off by what? By supervision machine. Yes?
So when it does this, will it actually give you out an equation?
No, no. It will give you some kind of numerical approximation. And for example, if you use the support vector machine, which can be treated as a special case of neural network, you can try to write down some kind of equation using the so-called RBF kernel. So once you train the neural network, the weight is determined, you can actually go down to write down in detail what would be the approximation like. But the weights or the slope, I should say, the slope or the weights of the neural network are estimated by the machine. So they are not in any closed formula. But once you use that weight, and basically it tells you if you use the deep neural network only using sigmoid function to approximate a function, then that function can be written purely in terms of sigmoid function. But there are a lot of coefficients. You don't know where they come from. They come from gradient descent using your solution. So the short answer is it's not a closed clean formula, but you just find that your unknown function can be approximated by sigmoid function and its composition through some unknown coefficient fitted by the network itself. So this is very powerful. And so this is why neural network become buzzwords. But the difficulty with neural network is they have a lot of local minimum, just like k-means. Neural networks loss function will always involve many different local minimum, and the technology of 1990 was too slow to solve it. After many improvements, the classical gradient descent nowadays become very advanced. So people nowadays do not use the classical gradient descent algorithm. Use many variants of gradient descent to feed the neural network. And now the convergence will improve.
Stochastic descent.
Even more advanced than. So I think like 8 years ago, there were already momentum descents, momentum model, and also the adaptive momentum model called ADAM. So there are many versions of model, or they are all based on stochastic gradient descent, but make improvements and based on some techniques in time series. So nowadays nobody uses the classical gradient descent, but that concept remains very important because it's the grandfather of all the techniques we are using nowadays. So now I'm right now giving you a general introduction of the neural network. So after introduction of backpropagation algorithm, I will look or talk about the multi-layer, the dense neural network has been a fundamental tool to handle nonlinear regression and classification tasks. So you can use the dense neural network to just do a basic nonlinear regression and nonlinear classification tasks. So our PML, in theory, should also include a lecture on dense neural network because it's also a legitimate approach. And that approach is based on stacking. You stack many layers together internally and then treat it as an organic algorithm and to train them. Usually, people classically use the sigmoid function as a nonlinear function, or somebody use a tangent, hyperbolic tangent function. And then different neurons are combined horizontally into layers.
Isn't that where we use ReLU as well?
Pardon?
ReLU?
The ReLU is a rectified linear unit. E is another function. So classically, people use sigmoid or tangents, but the sigmoid function have some problem that is going to asymptotically flat, and it become an issue later. I will talk to you about sort of vanishing gradient problem. So recently, people like to use the rectified linear unit. So yes, I would also add a rectified linear unit. So right now, that's become a more popular choices. But that function itself is not smooth. That function itself don't have derivative at one point. So classically, that 20 years ago, people didn't know how to do it. But right now, people have methodology to bypass the problem. So even though the function is not differentiable, it can still do gradient descent, some kind of sub-gradient method. So people can deal with that. So because the technology is more mature, and that become also something we can deal with. So classically, people use sigmoid function or tangent function and combine different neurons into a layer, and different layers are stacked together. You learn about stacking in your project, but more naturally, the neural network are stacked together layer by layer. the easiest kind of neural network is the logistic regression or multinomial logistic regression. So when you degenerate a neural network into one single layer, no hidden layer, it becomes the so-called logistic regression or multinomial logistic regression. So just let you know, the logistic regression is not trivial. It actually is a degenerate case of neural network. And the neuron, the basic unit of the neural network called neuron, is try to mimic. This is what a biological neuron is. If you look at under the microscope, our brain cell usually have an axon output. They have many different inputs, and this is a cell, the nucleus. And you accept input from here, and once the input come to certain kind of combination and then go to certain threshold, the axon will fire a signal out. So this is a biological neuron. And what the machine learning or deep learning neuron try to do is try to mimic the behavior like this into the so-called mechanical neuron. So over here, I mentioned that in the 1990s, early 1990s, mathematicians discovered that neuron can have the so-called universal approximation property that it can approximate a mapping from Rm to Rn arbitrarily well. So for that reason, you can also use the neural network to do dimension reduction. So neural network can also recover PCA. You can completely do a PCA using neural network and do a nonlinear PCA using neural network. So neural network can do a lot of things. So it happened that this is a single neuron over here. It accepts, this is a bias term, which usually is augmented by 1. So you try to view this term as the same as these other terms. Each term corresponds to one feature, and the feature input to this neuron using a slope coefficient that is called weight in the deep learning terminology. And then you have different weights over here, and then you accept this input, and then aggregate them linearly, and through a nonlinear function, this is called sigma over here. Classically, we use a sigmoid function. So now what you're doing is that you have a bias term or intercept term plus the features multiplied by the slope term. The combination is linear, but then after that, x by the nonlinear function, then decide the output. This is what the mathematical neuron try to do, is try to mimic this picture over here. This is the output and a lot of input from different. So that your cell in your brain the cell count is asymmetric. This is the output, and the output will go to the input of the other neuron. So they stack together naturally in your brain. And the picture can be more complicated, but this is the basic idea. How do you use the mathematical neuron to have a model on how does human brain function? And so this is the basic unit of a neuron. This is input, neuron, output. And this is a picture of our brain cell, that its brain cell is firing the signals. So all the different neurons are interconnected to each other. And that's how your brain become functional, can do a lot of complicated tasks, even though each cell itself is so simple. But if you combine it together, then you can do a lot of complicated stuff. You can memorize, you can compute, you can sing, you can breathe. Everything depends on simple mechanisms stacking together. So this is the basic idea. The basic unit can be very simple, but once you combine them wisely, you can do very convoluted tasks. So right now I'm showing you over here is that this is a neuron, and this is their different inputs. This is a second neuron. We also have same input, and this is a third neuron, same input. But the only difference is that you put the age, but from the input to the neuron, and each age is associated to a weight or a bias. Weight and bias, and different age can have different weights. And now you can try to tune the weights using gradient descent and try to make sure a given input and a given set of outputs, the output over here have to go through a nonlinear function. Usually we use a sigmoid for simplicity. So this is a bias, and that's the weight. So you tune your weights and the bias such that the output and the real target has the minimal loss. The loss usually in the regression setting is RSS. You want to minimize RSS. So this is actually how the neuron behave. And what they approximate is a mapping from 1, 2, 3, 4, R4 to 1, 2, 3, R3. So this neuron will try to approximate a mapping from R4 to R3 using smooth function, which is a sigmoid function and linear function. Yes?
When we learned this as logistic regression.
Yes.
So how can we use RSS on logistic regression?
No, when you do a logistic regression, you are using logistic regression for a classification task. When you are doing a classification task, because the label issue, you are going to use the log loss. It's okay? It's okay? But the same formulation, you can use the nonlinear function over here and treat it as a nonlinear regression problem. If you do a nonlinear regression problem, not to approximate probability, then you can use RSS as your loss function. The key part is not that you cannot use RSS for logistic regression. The key part is that in the context of RSS, you are estimating the probability, just like you are estimating the probability of the horse race, right? Because that must be a probability, you have to use a sigmoid function. And use RSS in the context of the probability and sigmoid function is not a good fit. Because RSS doesn't know about whether the function is probability or not. It could be the RSS is small, but the approximate function is not a probability. It goes beyond 1. It doesn't know. And therefore, it's not a good gauge. The better gauge is use your log loss. You penalize heavily if you try to approximate a function which is not a probability. That's what happened in classification task. But right now, if I do I'm not specifying I'm doing a classification task, you can treat the sigmoid function as the nonlinear function and treat the target as using the RSS, which is fine. And this is an example of the neurons or layers. So this is one layer, and this is another layer of neurons stacking together, such that this is actually an output neuron, but it feeds into the next layer, become the input of the next layer's output. And this is the final output. So this tells you, start with R3, 3 dimension, you jump to 4 dimension, and then jump to another 4 dimension, eventually collapse to 1 dimension. And so in terms of mapping, you have R3 to R4, this part, R4 to R4, this part, and then R4 to R1, this part. So this is the methodology is by stacking. You stack this layer to this layer and to this layer. You can see that right now we are doing mapping composition. We composite this mapping here with this mapping from here and to this mapping in order to get from R3 to R1. So this actually tells you something that's intrinsically inside deep learning, functional programming should be very important. This is a function composition. Functional programming happens very, very intensively in TensorFlow. And that's one reason, because the tensor composition happens naturally inside a deep learning neural network, which is a feed-forward neural network. And this neural network is called feed-forward because this graph is known as the directed acyclic graph. The graph over here is directed, that means you have an arrow, but inside the graph there's no loop. There's no directed loop. You cannot go from here to here and go back because there's no closed loop inside the direct acyclic graph. This is called acyclic, no cycles. The direct acyclic graph is an important class of graphs inside the machine learning discussion, and the feed-forward neural network is the one example that corresponds to the direct acyclic graph. And it's called feed-forward because this arrow over here gives you a direction from the input to output. It will give you a so-called information flow direction. So information will flow from this direction eventually to the target. And what does backpropagation means? It means you should, when you want to check whether your loss is good or bad, Suppose you have a random weight over here. You want to use gradient descent to change your weight, and you want to say the weight improve or not improve. You want to check the outcome. How do you change the loss? Then the loss will backpropagate to this side and affect how do you change these weights, and backpropagate it to this side to change the weight over here. So if the weight change is propagate against the information flow. That's why it's called backpropagation. It goes against the direction of the information flow. Any question? So the backpropagation algorithm is actually usually done by the chain rule, So I don't need you to actually understand the basic mechanism, just let you know that this is a basic underlying mechanism for a neural network to work. I think a few years ago, in some cohort, some students actually do a presentation on the backpropagation. But the derivation is kind of tedious for non-math people. So this is another example that the input layer is 3 dimension, mapped to 4 dimension, 4 dimension, mapped to 2 dimension. So time is up. Let me give you a 5-minute break. Let's resume after the break. Resume at 3:08. Let's resume at 3:08. Okay, time's up. So let's resume to discuss what is R. What is an RNN? What is the difference from the feed-forward neural network? So this is another example of the feed-forward neural network that you have 3 neurons, input neurons, and the hidden layer 1, hidden layer 2. So these hidden layers are not touched by the input and output, so they are called hidden layers. So the 3 to 4, 4 to 4, 4 to 1. And this is feed-forward because there's a definite direction of information going from the input to output. So, and then the backpropagation will go against the information flow, and that's called backpropagation. But for RNN, it's different. In a recurrent neural network, this is not the most general recurrent neural network, but this is a situation that you are allowing to have a loops. That the next layer of neurons, so this is the first layer, second layer, third layer, the neuron can affect itself, have self-feedback loop. Or you can use the next layer to feedback to the previous layer. And that kind of thing is never allowed in a feed-forward neural network. So once you allowed it, it's called recurrent neural network. And why people consider this? There are many reasons. First, people find that in the brain cell of humans, they also have that kind of feed-forward structure. And that's another recurrent structure. So the human brain cells do not feed forward only. They can go feedback to an earlier loop layer. Also have self-feedback behavior. This kind of behavior should be useful. Another reason is that in the 1980s, who actually was the inventor of the recurrent neural network? The earlier inventor of RNN was psychologist. So it was invented by psychologists. They wrote long paper, 40 pages long, 50 pages papers to argue this is the good architecture or model to model human brain behavior. But after the introduction of this architecture, they found that it's so difficult to train. And the earlier attempt to train the RNN almost failed. I will tell you one reason. The direct reason that at that time is because they knew how to do backpropagation, but for this kind of neural network, what is back become nonsensical. The direction, this is forward, but Gaussian distance is also forward. So which is forward? Because this kind of graph have loops. This introduces ambiguity. There's no definite direction going from input to output, and therefore the traditional backpropagation doesn't work. So people first have to invent a way to bypass it, and that method is called backpropagation through time. Backpropagation through time. Only after introduction of this concept, people can use the analog of backpropagation to handle RNN. What does backpropagation through time means? The basic concept is called unfolding, or some people call it unrolling. What it means, I give you a simple example. This is a very simple example of the feedback of the neuron by itself. This is the input, and this is the output, and the neuron about to have a loop to itself. In that kind of situation, the neuron, this is a simple RNN cell. It's only one cell of RNN. In this kind of situation, because there are the feedback loop like this, you are not allowed to use the backpropagation. Then what can you do? You can play a cartoon, try to unroll or unfold a single cell into a sequence. This cell, with the cell loop like this, can be replaced by a cartoon of timestamp. Notice this is only one timestamp here, but now you have x0, x1, x2, xt, such that all these neurons are identical to each other. They are identical copy to each other, and then you feed forward from this neuron to this one. This age corresponds to this age here, and the next one corresponds to a second loop, and the next one corresponds to the third loop. So in that way, you can unroll the circle over here into an array of neurons, and in that new graph, there's no loop. Yes?
Do you do it, you just basically make it like a for loop, so we'll let it go back and forth 10 times in this spot?
In a sense, yes, in a sense. But you will see that later, one way to implement the INN in this way is to use the while loop construction. We'll show you in the lecture code. But this neural network is much larger than the old one. But for this one, even though it's non-standard, you can still try to apply backpropagation to this big neural network. How many timestamps are there? They can be infinite. So backpropagation through time does solve the original problem on the original feedback loop, but it creates a new problem. Because this neural network becomes very, very deep. How many layers are they? If you use 1 million timestamp, that'd be 1 million layers. If you use 2 million timestamp, there are 2 million layers. And then there's a well-known problem, even in a feed-forward neural network, if there are too many layers, there's something called vanishing gradient. The vanishing gradient problem already occurs in the feed-forward neural network if it's deep enough. What happens is that each time when you do a feed-forward backpropagation, you have to use a chain rule in mathematics. You don't need to care about math. But each time, because all of these neurons or weights are identical, so each time you have to multiply your loss or your difference between the target and your true value or predict value or true value, the error or the residual, by a number to go to the next step. And the gradient descent will go to the next step. Go to the next step. Each time you have to multiply by a number here. If you multiply many numbers like this, it turns out the number either will become very, very small or very large. Like if this is 0.1, 0.1, 0.1, 0.1, you multiply 10 times, it becomes 0.1 to the 10th power. If it's 1.2, then you multiply 1.2 many times. The number tends to blow up or shrink to 0. This is known as a vanishing or explosive gradient problem. And this problem already exists in the feed-forward neural network. As far as if the layer, there are too many. And now the problem is even worse because in the INN, if you unroll it, the number of possible layers, there are infinite possible layers. Yes?
Isn't that why you don't use the sigmoid function?
That's one reason sigmoid function is unpopular lately, because near the both ends it is asymptotic to be flat, and then at that region it's easier to have the vanishing gradient. Yes. But the problem you mentioned is different from this problem. Both are caused by vanishing gradient, but different mechanism. So this tells you that backpropagation through time solves the problem of the feedback loop, but introduce one new problem is even worse than before. Yes?
Sorry, can you please re-explain that part quickly?
Yes. First, you unroll this cell into a chain like this, but in this process, you are developing a neural network with many, many layers. How many layers are they? If the timestamp is up to 1 million, there are 1 million layers. If timestamp is up to 2 million t, then it becomes 2 million layers. In that kind of situation, the vanishing gradient or explosive gradient problem becomes very, very severe. That each time, when you use the chain rule to backpropagate, multiply by a number, small number multiple times, tend to make your signal very, very tiny at the end. Or if the number you multiply is very, very large, tend to make your gradient descent on the earlier layer very unreliable. Either go to too large or too small. So this problem, yes?
No, that part was okay. Just on slide 35, how do you go from the left part to the right part? I understand the process.
Oh, the process is that you imagine you not only have one single copy, but have many identical copies. You replace this edge, so you replace the self loop. Because this is ICO, I feed back to myself. And then I create ICO 1, ICO2, ICO3. They are identical to each other. And the ICO1 talk to ICO2. ICO2 talk to ICO3.
I get it. Okay.
In that way, you bypass the problem of loop. But now your network becomes huge. And then the vanishing gradient becomes severe. And then people don't know how to do it. So for quite a long time that the people struggle with the INN but didn't know how to do. Then it comes the rescue is a long short-term memory neural network. Long short-term memory neural network replace the simple cell by something which have internal structure. So this is a cell in long short-term memory neural network. Itself has internal structure, and therefore people sometimes call this a smart neuron. The neuron itself already have internal structure. And the structure is controlled by 3 different gates. The sigma means sigma function here. It's using tangency for your signal purpose, but there are 3 gates controlled by sigma. I can turn on and turn off the gate. When you turn on, I use a multiplication to control, to let the information flow. If I turn it off, I can truncate the information here. So the information from the previous cell cannot flow here if I decide to turn it off. Same information. If I turn on the gate over here, the information can be multiplied and come here to combine with something from before. If I decide to turn it off, becomes 0, then information cannot flow, and the information over here can just go here without adding with the information from here. So they are complicated structure internally. And what's the goal? Is to introduce some kind of internal memory in the cell, such that the cell can memorize things from the past. And what's the purpose? If the cell can memorize things from the past, the vanishing gradient problem will subside. Is okay? So if you can keep memorizing something over here, then the information will not get lost in backpropagation as severely as before. So at that time, people invent the architecture just to solve the problem of vanishing gradient. But it turns out as a byproduct, the introduction of the memory is such an important idea. It nowadays become the main idea, which boosts in a lot of deep learning tricks. And a lot of people use chatbot. I'm not an expert in chatbot, but chatbot under the hood are using long short-term memory neural network. You can make a machine respond to human beings, answering questions. In some of our alumni, they get hired into Pfizer, and they have the AI team. And what they want to do is that when a customer asks for information in drugs, and the chatbot can respond, providing the truthful information without really have a human being behind. So they were building in-house, and I asked how many people were involved. They actually may put 20 people to do their projects. More high-end chatbot that you can answer medical questions to, and so after you graduate, depending on where do you land a job, the job demand, the requirement can be totally different. I would think that that particular student, when they got a job offer, he didn't know that this is the task. And it turns out, he told me that he could not use any package at all because what they want to do, there's no package doing that. They have to do everything from scratch. So let me show you some cartoon on the, so this is the basic INN. So this is the input, and then there's a nonlinear function coming here, become a hidden layer. The lag value means the lag 1 value of the hidden layer concatenate with the input, feed into the nonlinear function f, and eventually the hidden layer go to the output through another nonlinear function. So for INN, the structure is kind of relatively simple. But what happened for long short-term memory? So I'm not going to explain in full detail the mathematical structure of long short-term memory. So it can take a whole lecture to explain what is going on here. I don't think it's worthy. We don't have the kind of time budget. But let me just show you that in terms of that in the long short-term memory cell, there are 2 important variables. One is called H, the hidden output, and another is called C, the memory cell. The C, memory cell. You also will see this in the TensorFlow code. So you will see the hidden output and the memory cell. The introduction of, because this kind of C didn't appear in the previous discussion of RNN. So this is a new introduction of the long short-term memory. The introduction of the memory cell. And the memory cell can choose to forget or remember whatever information passed by in the past. So this is the key part to have a long-term memory. And that's the corresponding graph, that the input of X go to something in the middle, and then it feeds into the memory cell, and memory cell can feed back to itself to a lag value. Combine to feed to the memory cell, and then go to a hidden cell. And the hidden cell can lag one value, the lag one value of the hidden cell combine with the input, go to C tilde, and then go in this way, go to H, eventually go to O. So the picture is slightly more complicated than the basic RNN, but in terms of architecture, the plot can be very complicated. So it's even hard to memorize what the Z graph is doing. But right now, these three means that there are three different gates you can turn on and off, and controlling three different places how do information flow or not flow through certain kind of gates. So this is the main architecture of long short-term memory. So I wrote everything in mathematics. There are three different gates, and I can analyze the mathematics, but I don't want to spend so much time to talk about all these details. But later I will just move to the lecture codes. This is, let me remind you, this is just one cell. This is not a long short-term memory neural network. This is just a one long short-term memory neural network, smart cell. Many of them chain together to give you a network. The funny thing is that a lot of people try long short-term memory and try and Keras. So the one reason I decided to use TensorFlow with this lecture is because I read some people's blogs and they use Keras. And it turned out the person is not very knowledgeable. And he decided to tune the parameter. Eventually he's using one cell, train one cell, and to write 3 blocks. And he claimed himself to use long short-term memory neural network. Only use one cell. It's kind of nonsensical. Because the long short-term memory neural network is the chain of a lot of cells. But he only used one smart cell, and then he trained 3 and wrote 3 blocks already. And the whole thing was wrong. But I didn't know. So that's the reason I didn't want to use Keras, because it's very confusing for new beginners. And let me show you a few special cases. So this is a general picture how do different components interact with each other. The key part is the H and C. C is the memory cell, and the H is the hidden output. So from input to output, this part is what RNN is doing. But this part is the addition of the long short-term memory. In the extreme situation, you can turn off the interaction between the cell that you have other extreme situation. For example, if you decide to turn off this switch, imagine there's a switch off. Then your information come here and cannot go anywhere. And the output the hidden output can come here, but they cannot feed to here. And the memory cell will keep on memorizing all memory and cannot interact with the output. So this is an extreme situation that the memory cell is totally decoupled. It's like a person is memorizing all things and it have no interaction with the outside world. This kind of behavior is allowed in long short-term memory. It can do this kind of thing. If you decide right now the information I see had no relevance to the target, I decide to block it away. I only use my old memory, use it for learning. Or you can also have other situation that the hidden output and the input, the left value of it combine but cannot fit to the cell. But the cell over here keep on interacting with the memory cell over here. This is the feedback loop going on. And it can go into the hidden unit and go to output. So there are situations like this. You can depend on how do you control your gates. Remember, there are 3 different gates you can control over here. I wrote an equation of these 3 different gates over here mathematically and graphically. There are 3 different gates. You can turn on or turn off. This signal is multiplied on the line to make sure the information flow through or not flow through, and partially flow through. So this gate control, 3 gates multiplicative are controlled over here. And you have different kind of behavior. The cell, memory cell can be, as I say, totally isolated from the outside world, cannot influence the output at all, but have only internal memory. You can just let it loop. So if I decide for the next 100 time sample, I decide it's no relevance. I just keep my own memory fresh. Or I can also use my memory to affect the output, but input itself has no use to the output. This kind of behavior are possible. So I don't want to spend the whole time to talk about GRU, which is a newer generation simplifying the long-short-term memory in the sense that it removes the memory cell from it and still have the architecture to do something that the long-short-term memory neural network can do. So GRU is a simplification of long-short-term memory cell, and but playing a similar role. So that's why I want you to know. So from now on, I want to spend most of the time in the lecture codes, because I do think that it's worthy to spend some time in the lecture code. So in this lecture codes, we'll start from scratch. For the reason I just talked to you before, it's unwise to train you with Keras and have very confused concept. So I don't like that people kind of roll 3 blocks and eventually only train 1 neuron and call it a day. Say I train long-short-term memory neural network. It's not right. So I will start with the foundation, which is the TensorFlow's RNN cell. I tell you what is the TensorFlow RNN cell, and this part is missing in Keras. But later I will show you how Keras handle long-short-term memory. So I load different things, and I try to probably set login to info to prevent it print out too much information. So in TensorFlow, there are various kinds of RNN cell, and there is the so-called basic RNN cell. It's a classical RNN cell that we talk about. You also have a basic STL on short-term memory cell, a long short-term memory cell, and GRU cell. There are 4 different kinds of so-called smart neurons. Smart neurons means the neuron itself have internal structure. And the basic RNN cell is the most basic RNN design. But what's the distinction between the basic long short-term memory cell and the long short-term memory cell? This is the design who was invented in 1995. Original design. And later, the newer generation of long short-term memory cell add a lot of whistle and bell. And the newer generation is implemented over here. This is a modern version. This is a classical version. And the GRU, as I say, is a simplification of long short-term memories, but have a similar kind of functionality. So right now I'm setting my number of units equals 3. Then I construct, for example, a basic RNN cell. I set my number of units equals 3. So this number of units will control how many output do I get. A single neuron can have multiple dimensional output. Depends on how many hidden unit you want. So you print out, when I set number of units equals 3, the cell can have the attribute called output size. The output dimension becomes 3. So it doesn't output a scatter, a number. It output a 3-dimensional vector, depending on how many units you want. Because remember, the cell itself is smart. It has internal structure. And what's the state size? The state size refers to H we talked about earlier. The hidden states, also 3-dimensional. So both of them are 3 or 3. If you look at the cell over here, So I need to go up, sorry. If you look at a cell, you can allow you to take input and also states and scope, etc. So funny thing is this cell, basic RNN cell, in Python, the cell itself is an object. But the cell itself looks like a function that it can accept variables as inputs. Why is this? So if you look at carefully, if you tell this cell, you will find the most significant attribute is this guy, call. This guy call. What does call mean? This is a concept in Python. When an object implements a method called call, underscore, underscore, call, underscore, underscore, this object then is called callable. What object is callable? That means this object behaves just like a function. You can treat it as a function. You accept input variable just like a function, even though it's not a function type. If you look at the type of this guy, of this cell, is the TensorFlow RNN cell type. Basic RNN cell type. It's not a function, but it behaves as a function because it's callable. You can call that cell just like a function. So this is actually very important, that in TensorFlow, all these objects are callable. You can call a function just like you are calling a function. Is it clear? So there are a lot of summaries on the basic RNN cells, and the object is callable, and it will spit out a tail contain an output and also the states. So the input, you can input into the input feature, input states, and the scope is something which control the so-called area codes of the variables. It will spit out the output and output states. And batch size will refer to the number of samples. In other words, such a cell is in general a nonlinear tensor mapping from R to an input dimension, tensor with R, the state size, now state size equals 3, go to R, output size, tensor R, state size. So to facilitate this nonlinear mapping, that's what the RNN cell try to do. And the so-called batch size in TensorFlow means the sample size, means sample size. I also explained to you or emphasize that why functional programming paradigm is used very heavily here. What is functional programming paradigm? Functional programming paradigm, if you want to give examples, is the one you use in Python, the map, reduce, filter, that kind of stuff. Why is it that kind of stuff? The functional programming language treats the function as the first order citizen, and everything else is built on functions. And TensorFlow try to mimic it, try to make object callable, just behave like function. Why is that relevant or important to us? It's because the tensor mapping naturally can be composed together. If you have one tensor going map from here to here, you can have another tensor mapping from here to here. You can naturally composing them together. And tensor composing become a very, very elegant way to structure stacking of neurons together, and therefore become very important paradigms for deep learning to use. So either Keras or TensorFlow would support the functional programming paradigm very heavily. And another reason is functional programming paradigm is automatically lazy. The function doesn't do anything until you call the function and ask it to do it. The definition of function doesn't guarantee the execution of it. At the moment you define a Python function, it do nothing. Only when you call the function, you begin to execute it. That kind of lazy behavior, as I told in the first TensorFlow lecture, is very suitable for deep learning. Why? Because in deep learning or in database management or in big data, the Spark, the basic foundation is the human being doesn't know what they are doing. The input, the task they give to machine is inherently inefficient, often very inefficient. Therefore, machine is not going to follow you step by step. Instead, you are going to analyze your overall goal and find something equivalent to yours. And the lazy evaluation become important step in the process. Because you are too aggressive. You do whatever the human being asks you to do, line by line, is inherently slow. Is it okay? And now I'm comparing TensorFlow with Keras using these two pictures. And this is TensorFlow. And some of you probably noticed this is the breadboard. You can add CPU or IC chips and use the line cable to hook up different kind of IC and to actually form the electric circuit. And you can remove them and add another one and change the wiring and design totally different kind of electronics. And TensorFlow allows you to do this. And this is TensorFlow. And let's make it so complicated. In contrast, this is scikit-learn and the Keras. You have a well-defined interface and the EDO camera. How do you shoot a picture? Just press a button. Fit. That's what we call fit. And predict. By using these two functionality, you pretty much can do whatever thing. You don't know what's contained inside. What's inside the camera? I don't know. I press the button. That's why I call EDO camera. And you can still do a lot of things with that. I'm not trashing that. Because I shoot picture for my family using that kind of technique. So this is what Keras and scikit-learn try to do. Well-designed interface, but you cannot do anything not intended for average users. If you want something more advanced, I'm sorry, everything is sealed up. They don't want you to break it. So that's the different design philosophy between TensorFlow and Keras, or even scikit-learn. So therefore, when you try to jump into TensorFlow, truly want to learn the TensorFlow, you will find that you begin to feel frustrated. Because if you are used to this kind of paradigm, believe everything is so nice, iPhone, your camera, your cell phone, your TV, everything can be pressed by button and remote control. Now your whole world collapses. You have to relearn and rebuild confidence, and it takes time. That's why actually I discourage you people to spend too much time in TensorFlow in the bootcamp, because you only have 2 or 3 weeks. But it's a good add-on. After you get a job, come back or take a deep learning course and build up your foundation in deep learning. Maybe it's the future for your career. As before, let's try to illustrate how do you act on the cell. We put a placeholder. A placeholder means we do not know the value at the moment we design. The placeholder let TensorFlow know that we want to place a NumPy array of tensor object of float 32. The reason, I remember Michael asked me, why do we need to specify float 32 or float 64? Because they occupy different memory amounts. I need to know how many memory you want. The shape, why do we allow none? Because at the moment of design, I have no idea how many samples I use. This refers to batch size. At the moment, I don't know, but I know that I want input dimension is equal to 3. And the state input is also a placeholder. And then my design is to insert my placeholder input, my state input, into the cell as if the cell is a function. Remember, the cell is only a callable. But in Python, any callable can be treated as a function. So this syntax looks like a function. You call it, you spit out the output and the state output. And the state output can go to the next state input if you have multiple cells. Right now, we only have one cell. Only train one cell. This is called a compilation stage. Then in the computation stage, as before, we do a global initialization of all the variables and start a TensorFlow section. And this is a sort of context manager. After this loop, after this block, the section will be shut down. And how do we specify our x, which is the placeholder? We don't know what's the value, but at this moment, we use some kind of NumPy array, reshape it into a correct shape. Now 25 means I have 25 samples. 25 samples. I feed the value, and the state input, the input hidden state, I use 0 vector to input it, put into a fit dictionary. Then I run or evaluate the output, which is this guy. When TensorFlow look at the output, come here and know, oh, you want to execute this line. Then you use the fixed dictionary to insert into the X and the state input and call the cell. Now, because it's lazy, you only evaluate at this moment. Once you get it, you spit out the outputs and you also spit out the state out. You can actually combine these two lines into a single statement. Output and state out put into a list, you will spit out both at the same time. So I'm doing in less efficient way. So in this way, the neuron spit out something which is a garbage. Like this. But you notice the value is actually between -1 and 1. And this is not a coincidence. This is because this neuron, I use hyperbolic tangent as my activation function. So if I use a sigmoid function, you should go only between 0 and 1. So right now the output is between -1 and 1. And it's because I use hyperbolic tangent as my nonlinear function.
Where did you put that?
In the definition, original definition, if you look at the cell, if you look at cell over here, run it. No, not this one. Go down here. The cell is not in cell. It's in basic RNN. I should go to basic RNN cell.
Okay.
If you inside there's a default. There's a default there. You can change the default. Later we will change it for you. And you can print out this is the output and this is the states. You'll notice the output and the hidden state, they are identical, and that's not a coincidence. The O and the H, they are the same thing. Duplicate copy of the same thing, identical to each other. And with the same compilation, I can run a totally different data structure. Right now I can change it into 10 and rerun again. Now I can compute using the same graph. Each time when TensorFlow designs something, the compilation graph structure is compute and determined. But you can feed into different input. This time I change the input to 10 dimension, 10 samples instead of 25. I rerun it, you give me a different output. Only 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 dimension output and 10 dimension states. And how come there are 3 columns? It's because I specify the input dimension, the size equal 3. So initially, when I designed the cell, I already tell that the cell wants to have 3 dimensions. So it's over here. Output size equals 3. Because I set the number of units equals 3 here. I asked him to be 3 dimension at the beginning, so therefore he do 3 dimension for me. And now you can do the same thing for basic long short-term memory cell and the long short-term memory cell and GRU cell. You can construct in the same way. And the difference between the long short-term memory cell is the long short-term memory cell, when you print out, the state size becomes a tuple. Originally, for the IN, you only have H. Now you have H and C refer to the internal memory, which is missing in the basic RNN. In basic RNN, you already have a hidden cell, but now you have an additional thing called memory cell, and they have the same dimension as your hidden cell. If you specify 3 dimension, this is 3 over here, so both hidden cell and the memory cell will be 3 dimension. So the non-basic, the modern version of long-term memory also have the memory size, 3 dimension, hidden side, 3. So you can decide how smart your neuron is. Higher the dimension, the smarter is the neuron. More memory cell internally. It's a little bit like your computers, I mean RAM. How much RAM do you want? You want 3 units or 10 units? More units, the more expressive or more complicated the model or your neuron is. Of course, I'm not going to only demonstrate this. I will later use this to train models. So now let's use it to load the iris data set. And there are 150 samples because it's 3 dimensions. Why? Because right now, we are treating the 4th dimension of the iris feature as the target and the first 3 dimensions as the input. I use something called kappa. Why? Because naturally, this neuron only can output between -1 and 1. But I want something which can be comparable to the 4th column of iris. I need to scale it up. If I don't scale up, there's some kind of dimension mismatch. So I want to scale up my output from my neuron by 10 times in order to be comparable to the 4th column of iris data set. So that I introduced a number called kappa. If I do that, let me design my graph, reset my graph, because I have done some computation. Right now, I want to scratch it. I reset my graph, and then I design a few placeholder. X stay in, and Y is your target. Now, for example, I use a GRU cell over here. Then I let GRU cell accept the input and the state input and spit out the output and state output. And then, because there are multiple cells, the single cell, this is a single cell, have multiple output dimension. But final output of a target is 1 dimension. How do you solve this? My cell output multiple dimension, which is supposed to be 3, but I expect only get 1 dimension real number. How do I get it? I can compose it with a dense layer with 3-dimensional input and 1-dimensional output. In doing so, I can combine my result from the 3 hidden cells, so not 3 hidden dimensions, and combine them into 1 single dimension in my target, which is what it does. This dense layer does is actually combine the output of 3 dimension into a 1-dimensional input using tangency as my hyperbolic tangent. Hyperbolic tangent go from -1 to 1 as my activating function. After I do that, I have to scale this up by kappa. If I don't do that, there's no way that this guy is directly comparable to the iris data set's 4th column. I need to scale it up to larger number. I choose 10. I can choose 5. After that, I design a loss function using RSS. This is pretty much the MSE or RSS. The loss value is the mean of the square between the target and my predict output, scale up by kappa. If I do that, the final goal is to use the ADAM, Adaptive Momentum Gradient Descent Optimizer. I set the learning rate to very small, 1/1000, and then that's the operation I want to do. And eventually, I want to minimize the loss function. So this is the syntax to tell TensorFlow what steps you want to take. This is only descriptive. Internally, TensorFlow will decide what kind of gradient descent and how do you do it. But right now, you are going to give you a high-level sketch. And now, does TensorFlow do anything right now? It doesn't. It's still that easy. You say, okay, I receive your command, and that's your plan. I analyze your plan and draw a TensorFlow graph. And analyze what kind of graph is more efficient. But I stop there. I'm not going to do anything because I don't know what is your x. It's a placeholder. Right now, I don't know what is your x. How can I do any calculation? In the next step, you consider 5,000 epochs. 5,000 epochs means basically you run through gradient descent 5,000 times. Each time, you go through 150 samples. Each epoch corresponds to a complete feed of 150 samples. And you go to 5,000 times. You will know that 5,000 is too much. You don't need 5,000. And then, I use iris data set as my input. Use iris data set as my input. Sorry, I'm using the second to the fourth as my input feature. Use the first column as my target. And then fit into the previous operation. But then I evaluate the trend up. What is trend up? If you look at trend up, you go up. The trend up is this guy. It's the minimization step. Well, from here, TensorFlow jump up and see, oh, this guy wants me to minimize because I want to run the trend up over here using a fixed dictionary. So only at this moment, you know what data you want to use. I want to use the iris data set, second to the fourth column as the feature, first column as the input. And then I run 5,000 iterations. Each iteration, I go through 150 samples completely. Then I will evaluate and loop through and records the loss value. And I can plot it like this. So at first, the loss value is very, very high. And the loss value drops very fast to a value and stay almost constant. So if you look at from graphically, you will think that you only need to go through like 300 or 400 epoch will be enough to give you a good accuracy. And going to 1,000 or 5,000 is overkill. But at this moment, I just use it to illustrate. So right now, what we are doing is to train a smart neuron. Nothing to brag about. Don't tell people you are training a neural network because there's only one neuron here. But only thing is that it's slightly smarter than the average. So that neuron already have some internal structure, has some IQ, but you are only training one neuron. You can use it to train a machine learning algorithm. So you cannot believe people just do this and write 3 blocks. Say, I'm doing long-short-term memory neural network. And you can actually print out the states over here. So you can. And this the next is a slight different implementation that you can slightly improve using the previous run. If you are doing the epoch by epoch, you can use the previous epoch's run's output as the input from the next run, feed into the next run, and see how it happens. So you can slightly over change your code to facilitate that. And you can also see that the improvement of the loss function will drop even faster than before. Probably 100 epoch is good enough to have a very stable,
actually have a much higher loss.
Slightly higher in this case. Slightly higher than before. But because this kind of operation is non-deterministic, so you have to really run multiple times in order to make sure that it's really worse than previous one.
Not only the epochs, you mean running the whole thing several times?
Yes, because there are some kind of randomness involved. In the you shuffle your data in a uncertain way. So you, in a sense, your conversion will go faster, but you are not guaranteed to always get to. If you look at the minute detail, you can go slightly worse than before, but the effect you go to that place faster. And now we want to use the modern long-short-term memory cells as our building block. And the easiest construction in TensorFlow is use the while loop construction. Remember, we told you in the first lecture, in TensorFlow, there's a whole new way to write a while loop without a while. The while is treated as a function. That's a functional programming paradigm. While is not treated as a loop. Instead, while is a function which accepts another function. What function? A logical Boolean function to detect whether the condition is true or not. And there's a block function to detect what needs to be executed in the block. Once you use these two functions, the while construction, so you have the one condition, this is a Boolean condition, to check whether the timestamp is smaller than the window size or not. And the loop block is another function. Once you have that, the loop block will accept timestamp, output timestamp plus 1, input, output, and state. So it's like 4 tuple, come out 4 tuple. So loop block is just a function like that. Once you have these two constructions, you can, and internally in the loop block, you are using a long short-term memory cell. This cell is a long short-term memory cell in a loop. And this is what actually Michael has suggested. You can chain different cells together using a for loop. But instead, it's over here using a while loop. This is the most naive approach to do it. And and now, in the CS30 over here, I use TensorFlow's while loop construction. That's the function. This function accepts two functions, logical condition and loop block. And there are some loop variables which indicate which are the loop variables. Once you have this while loop, it will loop for you and eventually spit out the final answer. And that's the syntax. So how do you design a long short-term memory network? Is by using a while loop. The most naive way, use a while loop on a cell repeatedly. Remember, those cells are identical. The cells inside over here, they have a shared weight. It looks like this is a single cell loop many times. So when you do gradient descent, the weight of different cells are the same. So while loop will do a computation for you, and it's kind of quite efficient. But the code, unluckily, is ugly. The code itself is ugly, but if you get used to that, it's very fast. That's a naive way to implement. And you can evaluate the tensor. I don't want to go into detail, but just run the corresponding, evaluate the corresponding thing. You evaluate the tensor for you, the NumPy array for you. And then people say, well, is this always necessary? And you can make your life easier by using something called dynamic INN. The dynamic INN will try to do a while loop for you internally without you to do all the coding. And the good thing, there are two versions. One is called static INN, which will unroll everything at the compilation stage, which is slower. Dynamic INN has the advantage that you will try to unroll only when you compute. So the graph is compute when you try to do a computation, and you can have advantage to make it faster. So people prefer to use dynamic INN to replace the while loop construction, and this is very fast. What you need to do is input what kind of cell you want to use, either long short-term memory or basic INN cell. What is your input feature? Where is time dominate? Time major, time dominate. There are different formats. I want to use a time major format, true. And what's the initial condition? Initial states you put in. And the whole while loop will be done internally. So in this way, they become a one-liner. One line of code can replace whatever was before. And the speed is fast.
This is what Michael had to do for 0.72?
I don't think he do TensorFlow. No?
I don't know.
No, I meant Michael only do the time series in the previous two lectures. Today's lecture has nothing to do with TensorFlow. So therefore, I suggest you to treat TensorFlow as a jump start. If this happened in the coding challenge, I would treat differently. So this is called dynamic INN, and you can evaluate. And dynamic INN can accept the cell, what kind of INN cell. There are 4 different types. What kind of input. You can even specify the sequence length in advance, and there are many different attributes. Whether it's time major, default is false, etc. So you can actually do a dynamic INN and do a one line of code. So it's not too bad. The while loop is kind of ugly, but it's efficient. But you can do a dynamic INN, and it's equally fast. So if you want to build a long short-term memory neural network in TensorFlow, dynamical RNN is the way to go because you don't need to write too much code and you can achieve the same effect. And there are other ways to do it I'm not going to mention, called scan. There are other ways to do it. And now I'm going to demonstrate how would you do it in Keras. Remember, the famous library Keras have been absorbed into TensorFlow as a sub-package. So you can call Keras independently, but TensorFlow decide to support Keras, so you can treat Keras as an internal package. So that's the attitude I want you to have. And you learn TensorFlow in the process, one chapter called Keras. So in the long run, Keras will not exist as the standalone deep learning library because it's only right now a learning tool. Because in internal speed, it cannot be compared with TensorFlow. But as an education tool, it has a lot of value because it makes your life easier. As I say, the design is to make sure the new beginner learn things fast. It's like learn to use an idiot camera, just point and shoot. Yes?
So people in the industry would use Keras?
No, in the industry, right now people would routinely use TensorFlow. And I'm not saying Keras is totally useless, but its functionality is a subset of TensorFlow. And when you are doing an open project, it's hard to say how much would you need. If you are sure that that kind of thing can be achieved by Keras, you can still use it. But in the open project, you don't know what's the boundary, and then it becomes a problem. So people are generally, I think in college, people routinely learn the deep learning through Keras because it's a great learning tool. But at the first line of industrial application, people won't use it as an independent deep learning package.
And you say sklearn is like Keras, pretty much, right?
Yes.
So what's the equivalent of TensorFlow for other more simple machine learning?
That doesn't exist. But there's no such libraries which is similar to TensorFlow, which allows you to build a strategy from scratch.
So people use sklearn in the industry?
Yes, they do. But oftentimes, if they do warrant, because sklearn is open sourced, so you can hack it. You can hack it as you want. But if you only hack it, you still need to read the source code. Then you cannot just do a fit and predict. You need to go into internal and know how to design. So let's see how the long short-term memory neural network is implemented in Keras. I'm going to demonstrate two different kind of techniques. Inside Keras, long short-term memory is a layer. It starts out as a chain of neuron already. Is okay? There's no single neuron. That's the confusion. So the long short-term memory starts as the TensorFlow subpackage Keras. So right now, I think in an attitude, if you want to learn, just learn TensorFlow, and you can focus more on Keras if you are not happy with the TensorFlow inconvenience. There's the layers. Long short-term memory is not a cell. Itself is already chained together layer of neurons. It's already a lot of neurons over here. And you can specify a lot of different things like window size, input dimension, etc. When you specify the window size to be 1, it degenerates into a single neuron. Unluckily, this is what that person was doing when he wrote a block, 3 blocks. He specified this window size to be 1, didn't realize that it reduced to a single neuron, and brag about he was designing a long short-term memory. But what he was doing is only treating using one long short-term memory neuron to train machine learning model. But this is not the long short-term memory layer. So the whole layer, you can control window size and input dimension, and there are placeholder, etc. So there are different definitions. I mean, I'm not going to go to detail. But the interesting thing is the following. In Keras, there's a very well-defined API called Sequence API, which allows you to stack up the long short-term memory neural network into stack layers very easily. And the syntax is very convenient to use. So in the following, we are going to look at this nonlinear function, which is sine plus 0.2 square times 0.5. And the function looks like this: big wave, small wave, big wave, small wave. And later, I'm going to show you the second half only. The first 2/3, 3/4, will be used the trend set. And last 1/4 will be used the test set. And this is a deterministic time series. This is a deterministic time series. And my goal is to use a stacked 2-layer long short-term memory. I'm not going to use a single layer. I'm going to use 2-layer in Keras and to show you how to train it. And I think I demonstrate the syntax of Keras. It's very neat and very similar to scikit-learn. The way you do it, so there's a key part I want to show you. In Keras, there's a sub-package called models. In the sub-package, there's something called sequential. This is the way to tell Keras you want to stack different models together sequentially. Once you call the sequential, this is called your empty model. It will give you an empty model. And I want the state number. State number means how many internal memory you want. I want 25 dimension. So I want my neuron, smart neuron, to be quite smart, 25 dimension. And the second layer, I want more. I want 75 dimension. So each neuron already have internal memory, 25 cell and 75 cells, 75 dimension memory. So how do I add that layer to the model? I just append. This add is nothing but append. You can view the model as an empty list. You append an object to it. What object? Long short-term memory layer. And you specify the parameter. The second layer you add is another long short-term memory layer, but triple the state number. But you need to make sure the dimension match. Otherwise, when you compile, you will run into trouble. Then finally, because I have 25 or 75 different internal cell, internal dimension, I want to collapse it into a dense layer using a linear activation function. Activation is none, means linear. And the input shape is 3 times. The window size is the width of your time series. And how many input dimension is the dimension over here, is this guy. I have input dimension this, I will collapse into 1 dimension. Everything will, so many dimensions will collapse to 1 dimension. That means I'm using 75 dimension of wisdom eventually to produce 1 dimension output. Okay? Then I add this dense layer to the model. So then right now my model have 1 long short-term memory, second long short-term memory layer, finally a dense layer. And then I call the compile command. I compiled it using ADA gradient descent optimizer and loss function. I don't need to code it. I just say the loss function is MSE. So this is more convenient. Input a string. So once I do that, you can spit out a summary. This summary allows to tell how many parameters you have used. First layer long short-term memory altogether use 28,000 parameters. Imagine your first lecture on multivariate regression. You only use 10 parameters. You think you are doing something. Now even this layer are doing 2,800. The second layer is 30,000 dimension parameter you are estimating. This is a small network. It already have so many parameters. So you have to jump from the first lecture of PML, which is only 10 parameter, and decide, oh, you have done machine learning. Now it's 10 of thousands dimensions you are gradient descending. And finally, the dense layer will require you to fit 76 dimensions of parameters. And then altogether, how many parameters are involved in the model? It counts 33,176 parameters. All are trainable. That means they are going through gradient descent. Non-trainable parameter is 0. You make sure every parameter is not fixed. They can be tuned by gradient descent. Trainable means tunable by gradient descent. And now the next step is very similar to scikit-learn. How do you fit the model? You model fit, just like scikit-learn. And you input the feature and the target. You specify how many iterations you want. Equal means a complete run of samples. You do 1,000 runs, and each time you look at 50 sample size, 50. Batch size is 50. Do not verbose means do not print out the outcome. You can run it, and then you can do something interesting. You go prompt model, but this prompt model is slightly broken. You have to fix the TensorFlow code for one small part to make it work. It will give you an output like this. If you fix the bug in TensorFlow, it's not too hard, but you have to see the error message and go in to change it because there are some inconsistency. But I store the file as a PNG file and print out. This is the input layer, first layer long short-term memory, second layer long short-term, and the dense layer. It will give you a pipeline. You are stacking different layers together. And Keras allowed you to have this kind of plot automatically. It's convenient. And that's the outcome. So I'm saying the plot should start with 0, but I only plot this plot to magnify it. You'll see that the actual value is the orange one. Fixed oscillation, small oscillation, but the predict value in sample, the training part is like this, over a good match. But the out sample prediction, it knows that it need to bend. Given they only see that oscillation 3 times, the neural network is smart enough to believe that it had to bend, but it doesn't bend it in the right place. But remember, the data is actually, you only have 3 oscillations. If you look at the oscillation over here, there are only 3 oscillations. 1, 2, 3. And then you know that first one you should bend again. But it doesn't bend in the right place. But knowing that you need to bend already is not trivial because it doesn't see too many oscillations. And you can do the same thing using another API. It's called functional API. That means this is the second API of Keras that you can actually have long short-term memory 1, long short-term memory 2, and a dense layer, put an input layer, 4 different layers, input, long short-term memory 1, long short-term memory 2, and dense. And then how do you chain them together? Very easy. Input, because the long short-term memory is a callable object, you can treat it as a function, take on the input, spit out something. This something go to the long short-term memory 2 and spit out something else. And then that guy go to dense 1, go to output. So this is a basic function composition. Using this kind of syntax without using the add, you can also train a model. And the model eventually can create a model from input and output. If this is the input and this is the output, the model knows about input and output, spit out the model functional programming. Then you can compile using the same syntax before, and you can fit. And this time, doing a similar thing, you fit the model like before. And this time, the prediction is like this. If you do different run, the result will be different. So the orange one is the true solution. The fit now is slightly different. Sometimes you will give a solution which is almost fit, depending on each run. So because this is the right stochastic gradient descent, each time you are going to get a different solution. So I only use to illustrate that what Keras can do with, pardon?
I run it, I just fit in mine.
Yes.
And I got a great result.
Yes, because this is a gradient descent, stochastic gradient descent, so the result won't be the same. Yes, each time. So I run this probably a few hours ago, and most of the time my result is very good. But sometimes I just have, because it's stochastic gradient descent, no guarantee you will get the same result. So let me start the lecture here. I'm going to let me have a 10-minute break and come back to wrap up and talk about a little bit about TensorFlow itself. It's okay? Have a 10-minute break. Then come back at about 4:30, and then we wrap up within 10 or 20 minutes.
I'll never use it. Right? It's just, because they're practicing in a day, they practice what I practice in a week. I learned a lot, but it wasn't so practical. And I wasn't at that level, just intellectually, I'm not as big as him. It's like I need somebody who like more. The thing I have a challenge with Luke is Luke doesn't want to give the answer once you figure it out. There's not going to have much time left. I don't fucking figure it out. It's moving. So what's the choice? Maybe I got this. I don't like that. I do.
Like someone to nudge your vibration and wants you to just like that. Yes, and corrects you what's wrong with your vibration. That's how I but yeah, I get it. But I don't like
Trace. I don't know how many traces in that stuff.
that's how
I go to the stock market is very stuff. I asked him. It's not. No, he said the reason he does this is he wants his freedom. So, I get it, but he would, good question, he's still stock guy. I would love to mention some more time with those instructors. This next week, I think we take 2-3 hours each day and not work on the project or something. There was some stuff, so all the governance and experience and their series and some other practical stuff. But like I can't just ask myself what this, but it's probably important to improve. I'd be curious to see what David has to say about this stuff. He doesn't know stocks like this. Peter should dig in like worse than all. Well, I mean, it's. What sort of R? I don't want to go back to R. I think R doesn't even implement half this shit anyway. It doesn't. What's that? No, I know, but R. I don't think you can do this in R anyway. Arima, you obviously. Yeah, but I could do it. I know, but I want to learn. I've never learned this one. Alright, so this, you, I don't know how to. Stock specifically, I go to I go with it. No, it's rather small. You can ask that. Let's have this one. No, I definitely can't. I want to figure out how we can run on this project. I feel like we're still, not nowhere, but we're still far away from a viable solution. Yeah, but I feel like I don't even care if I present this over or not. Yeah, I know. I want to get it done too, but it's spend enough time on the project. I would just for myself like to know that I can do this problem, right? That you say, okay, not
obviously this is sports betting and it's not like the sexiest topic. But here you go, here's data I've been collecting for a while.
I 100% get it.
But I'm not there yet.
I agree, but I feel like I would still like to take 2 hours off from this. So next week it's 100% fine.
Looks like it, right?
So
Thursday.
it's a bit too much. I mean, I was hoping that we would have, it would be done maybe on Monday, the project, and on Tuesday try to build out like neural network, where we spend a whole day working on crazy stuff just to get experience on neural nets.
Yeah.
That would be fun, but I don't know, I would like to take a few more hours to work on this.
That's fine. I mean, time series is really cool.
Because next week's probably the least busy week for the teachers.
Yeah.
That's probably has some stuff on this one.
No, but you're right, it is.
I could not check for 2 days on Wednesday.
Did you guys already have TensorFlow installed for this lecture?
I've been using the Docker. Even that has been a little wonky, so I haven't been running any of the cells, and I've just been looking at the output that's there.
Yeah.
Because the other days didn't work.
I've installed Keras and TensorFlow and everything works fine. I just had warnings for future like degradation and stuff.
Yeah.
What do you get?
Fucking Windows, man. It's just such a so annoying.
Oh, it's more complicated on Windows?
Yeah. Like, it's just never straightforward for some reason. I mean, it's whatever.
Well, like,
But like, this is supposed to be like a simple.
it installs it.
Yeah, like it installs, but like it doesn't actually work. So.
Like, does it recognize the package there?
It'll go through, but like whenever I do try and run this, whatever I've installed here is just, I haven't installed it.
And it's like a big install or compact?
This pip install right now.
Yes.
And
TensorFlow?
instead of pip install.
I just did pip install for TensorFlow, it installed.
Yeah, but on Windows might be different.
I know mine works too. My Conda is weird, it takes forever to install anything, very slow.
Yeah. Conda thing is pretty weird. I like to put notebooks, but I won't.
That's true, but I'm hoping we're far enough along that we can forward.
I don't know what to do. Even videos, I tried live streaming here once today. I love it. It's constant. It's constant. Big stuff.
Something I don't like, I do not like working on a laptop, and that's why I start getting frustrated at the end of the day. The screen is so small, I have 2 monitors, trackpad. Plus it's also, you know, I get tired.
Okay, so time's up. Let's wrap up the final section of the lecture code. So we have demonstrated 2 different ways to use Keras, and one is through a more popular sequential API, and but more efficient one or more powerful one is to use the so-called functional API, because functional API allows you more flexibility to build a different kind of architecture. If Keras is so nice and so similar to scikit-learn, and why isn't the most dominant deep learning library out there? And after the introduction of TensorFlow, within a few months, TensorFlow become the #1. They are also competitors, but the Keras is no comparisons. And so eventually Keras is absorbed into TensorFlow. And what's the reason? One main reason is the flexibility. The reason that make it convenient is exactly the same reason make it inflexible if you want to change it. But for those experts who want to change it, they found the Keras design too restrictive. And the second is about speed. Even you build similar kind of model, the TensorFlow code will run much faster than Keras. Even though you use Keras inside TensorFlow, it will be slower because the design is much more robust in TensorFlow itself. For example, you will need to know about the window size at the time of your construction. When you are before you do comparison of the model, you will need to know how wide is your window size. And when you want to design your how many neurons you want to use, basically 20 neurons, 100 neurons, you need to decide when you are comparing the graph. But on the other hand, TensorFlow allows you to dynamically compute the graph when you unroll at the computation stage. So it allows you more advantage, and you will speed up the process. So Keras in terms of speed is not comparable to TensorFlow. And there's another thing is right now I showed you an example. Actually, there's a TensorFlow. There's actually one and a half year ago there was a Kaggle competition, and someone won the Kaggle competition using TensorFlow and as a winner to predict the Wikicyclopedia web page visitor traffic. It's misspelling traffic here, no E. And I'm not going to repeat because the code is very, very lengthy and a lot of, he had to use the full TensorFlow, and even the gradient descent is not a standard one. He had to use the gradient descent who was invented like a few months ago. In using that kind of technology, he won the competition because the competition was about predict the Wikicyclopedia. And there are how many time series? About 10,000 time series or so. And he was able to train us the TensorFlow model and win the competition. And one factor is about high performance, and also the second factor is about speed. Because the way he did it, the speed is much faster. And it's only possible if you use TensorFlow, because everything is well optimized. So I'm not going to show you the whole solution, but I only illustrate some simple example following the same line. But for example, a key thing I want to mention is, for example, how do you generate features from a time series? You can use the calendar. In Panda, there's a holiday calendar, and you can use to construct the holidays from the time series and use it as a feature. Which day is the holiday? Boolean, true or false. Use that as a feature to predict the web traffic. So as I have told you, in the time series content, most of the time you will need to use the external features, as usually called exogenous features, to help to predict. So if you just use ARIMA, oftentimes the prediction will be very weak. And I think that that winner of Kaggle, he used probably 100, less than 200 features, external features to enhance the prediction. I'm only do a baby version, so my result is very poor, but just let you know the process. You can use the calendar day, whether it's a holiday, as your input feature, or you can also use the weekday, Sunday, Monday, Tuesday, etc., also as your feature, as your internal feature, and move it into your input feature and train a model. And one key trick in TensorFlow is how do you stack two different long short-term memory layers together. In Keras, you either use the functional programming paradigm and you chain them together by composition, or you just pipeline pin them together using the first approach, that you add different layers together into the same model. You can view the model as an empty list. You append one long short-term memory network and the second one. They stack them together. But this is also the cause of the inefficiency of Keras. That everything is static, predetermined before you compile the graph, and therefore it's kind of slow. Even though you can, for large-scale computation, you become too slow. But for TensorFlow, you use a different philosophy. Instead of stacking two networks together, you actually only stack two neurons together. You have a smart neuron here. You stack another neuron together, become a two-layer neuron. It's okay? So this becomes a two-layer neuron. And then you do an unrolling later. So in the Keras, it first unroll the first layer into a full layer and unroll the second layer and stack them together. But TensorFlow do it a totally different direction. Do it vertical first. You stack two neurons together using something called multi-RNN. There's a function called multi-RNN I'm going to show you. They can stack two different layers together and then do an unrolling later through a dynamic RNN or through a while loop. How do you do it? The code is over here. You give it a list of the cells you want to stack, so you can do multiple layers together, 1, 2, and use the multi-RNN cell to stack them together into a fast cell. And once you stack them together, you spit out a new cell. This new cell already represents the compound effect of the both layers. So this is a fat neuron, the whole thing. And then you try to unroll it using a dynamical RNN. That's the approach. But the trick of using dynamic RNN is that the computation is done when you do unrolling. So it's not unroll before the computation. It's how do you determine the most efficient graph is on the way that you unroll it. You decide which graph is more efficient. In that way, it becomes, you can use the information later at the so-called computation stage to see what computation would be easier or faster to do. In that way, it will save you energy or save you time. So that's the basic philosophy in TensorFlow, and then with a compound cell, you can run a dynamical RNN on there to unload it into a neural network. So before there is only a cell, using dynamic RNN, unload it into a cell, a neural network, whole network, and multiple layer, and that's the philosophy. And if you want to use something called dropout, there's something called dropout you can implement individually, and there's a so-called dropout wrapper. Dropout wrapper. What does dropout means? Dropout means just like in random forest. Random forest allows you to drop some of the feature and only keep a portion of that. And TensorFlow or deep learning also borrow an idea. It's called dropout. So in training your neural network, in order to prevent overfitting, it will be helpful to drop some of the input legs. So just like cut this kind of legs loose. I freeze this leg. This is called dropout. I do it randomly. This is like random feature dropping. I drop randomly 30% of my features. That kind of trick is very useful in training image task that people use routinely. And in TensorFlow, you can wrap your TensorFlow cell by a dropout wrapper that allows you to do dropout, which is similar to random forest. You randomize your input features. That kind of technique you can do by wrapping here. But if you do it in Keras, you notice I didn't point out in detail. Dropout. Inside Keras, the long-term memory neural network already put dropout as a function, as the input choice. You can choose how much you want to drop out there. So you will try to train a model, only use 80% of the feature, input feature. And dropout 0 means you use 100% of the feature. It is etc. So that's the difference between Keras and the TensorFlow. TensorFlow actually uses different syntax to achieve the same kind of concept. So this is pretty much I want to say, but one thing I want to mention on Keras is Keras allowed you to, let me go to this side, to do research. So up to now we are only training in a very naive way, but what if you want to tune the hyperparameter? And it turns out because Keras is designed in the same philosophy just like scikit-learn, actually you can convert a Keras model into a scikit-learn model and use scikit-learn's research CV to do research. Of course, this is a toy because in real life, in a high-end deep learning, doing research is notoriously inefficient. So years ago, people already begin to use something called Bayesian optimization or other technique. What does Bayesian optimization do? Is try to jump through the space of hyperparameter instead of going brute force one by one. Is that I try 1 and 2, and then I'm going to jump to the most probable place, jump there, and then based on this evidence, then I go to the next place, jump everywhere. And then I can reduce the number of jumps and get the same effect. So in short, I will be able to get a good solution without going through the whole grid. There's a modern approach called Bayesian optimization. And
Why is it more accurate, or is it just faster?
fast, much faster.
Why do we keep learning research?
Pardon?
Why don't we learn that when we learn?
Because Bayesian optimization itself as a technique, right now is mostly using in either like in cargo for speed reason or in high end. There are only one instance that our graduate students went into industry, immediately they come back to say they are using Bayesian optimization. Most of our graduate students graduate, when they go into industry, they are not still using that.
But if you say it's faster, why do people still use research? Is there a reason?
But no, research is the theoretical, very sound, and it's the first thing you should learn, right? It's like, even though you probably at the end in college you learn calculus, but in elementary school you still learn arithmetic. You don't say I learn calculus, I don't need arithmetics.
Yeah,
and
About,
yes, but on the other hand, because the Bayesian optimization is faster, but on the other hand, it uses the philosophy of reinforcement learning. It's harder to explain. If you treat it as a black box, it's fine. But if people ask you, why do you think it will work? And it's difficult to explain. Just like in the bootcamp, we don't teach you reinforcement learning because reinforcement learning requires at least half a year exposure of time series analysis. So it's hard to do it, and therefore, but we need to tell you something, right? And the research is the most standard way to do it. If you want to teach Bayesian optimization, the basic requirement, the threshold is much higher. I would imagine if you go into industry and stay 1 or 2 years, come back, and then you can teach Bayesian optimization and also understand the rationale. And the people in the bootcamp have some history. Some people in the bootcamp did use Bayesian optimization to their project, but they treat it as a black box. That it's faster, but you ask me why? I have no idea. Because other people on cargo using it, I also use it. I don't think this is particularly helpful for your job search. But I say, in terms of sampling, I find only one sample of our students went to industry immediately. They say their company were using Bayesian optimization. So at this moment, we can still stick to research because research people does test you. It's unlikely people will expect you to know Bayesian optimization after learning machine learning for 2 months, 1 or 2 months. So at the moment, if people ask you about Bayesian optimization BO, you say, I don't know. It's not guilty. But if you say, what's research? You say, I don't know. People will say, you don't know machine learning. And that's the difference. Yeah. It's okay? Not that I don't like it. Actually, I did roll a Bayesian optimization, Jumpstart before, but never have a chance to teach it. Yeah. But just let you know, and you can actually use Keras model, and there's a raptor, scikit-learn. There are 2 raptors called Keras regressor or Keras classifier. It can spit out a scikit-learn regressor model and classifier model for you. And then you can use scikit-learn's research CV to do some basic research. So low-end model is fine. But if you really going to go to very high-end, and doing research is infeasible, too slow. And people do need to use the more advanced hopping techniques like Bayesian optimization or there are other techniques out there which can help you to hop. So research is inefficient. Is like finding a suspect as a killer. I look for this. Are you? And then it becomes very slow. And Bayesian optimization is like a good detective. Look at one evidence, and then, based on that evidence, no, this guy cannot be a case. And then I go to that guy, and that guy. It's much faster. But it's based on Bayesian statistics. So I think I want to end the lecture here. I can keep on talking and for another half an hour or 1 hour, but I don't think it will help you too much because I want to treat this as a jump start. I don't want you to focus too much on this yet. After you get a job, have a job security, and we feel very comfortable with scikit-learn and become very productive, you should enhance your skill set to deep learning because this is the future. I think after 10 years, deep learning will become shallow learning. So at the time, everybody will know that. But right now, it's still the cutting edge. So as far as getting a job, I'm not sure knowing TensorFlow will help you that much. Maybe you are able to get 1 or 2 good jobs requiring TensorFlow, but in terms of job numbers, it's not the majority out there. Because I think at this moment, we want to focus more on business application. And in the business world, not always the deeper or harder the model, the better. You'll find that eventually, whoever can find insight and make contribution to the business will count. And for that reason, people in different domains use different type of model. Some people only stick to linear model. It's perfectly fine. So you can imagine, even at Goldman Sachs, some of their team, when they predict default, they only use logistic regression.
I heard in the banks they have to because they have to be able to
Yeah, that's one reason, but there are also other reasons. Even internally. So even if they are trying deep learning model, it's only as a side tool. The main tool is still using logistic regression. They can compare, but officially the version always logistic regression. So it's not that the more advanced the model, you will become more popular. So at this moment, I still want you guys to focus more on the linear or model. If the linear model you are feeling comfortable, go to random forest, support random machine. And deep learning at this moment, you are something of luxury item. Some people may want it, but that kind of job may be very prestigious, but not great in numbers. But for entry-level job, the number counts. If you have 10 jobs wanting this kind of skill, it's better than one job wanting that skill, in my opinion, at least for entry level. But after you get familiar with all the tools, 3 years later, it may become my teacher, can teach me, then you should go ahead and move on to the next layer, next level. But probably not now for job search purpose. Because if you diversify too much, then everything becomes very thin. So I want you to spend more time coding, in data analysis. Once you are very strong in this, spending time in machine learning, the basic machine learning, more than to more advanced topic. But I think deep learning at this moment is a luxury item, yeah, in my opinion. Yeah. Okay, good luck. So this is the end of my lecture in the bootcamp. So I will just see you, and next week I think I'm going to attend your ceremony. So I should be here. So I will see you next week, and good luck with your capstone projects. Yeah.
Thank you.
Yeah.